When people talk about space, it usually starts with images that feel familiar long before we ever study them. The night sky looks like a distant backdrop, yet modern science treats it as an active medium, filled with processes that never really stop. Cosmic space is not empty in the everyday sense. Between stars and galaxies there are fields, particles, radiation, and the lingering signatures of events that happened long before any observer existed. The universe is described not only as a collection of objects, but as a system of interconnected scales. Distances are so vast that ordinary units stop being useful. Light, which seems instantaneous in daily life, becomes a tool for measuring time. A beam reaching a telescope carries information about how an object looked in the distant past. In that sense, every observation is a look into a portion of history that has already happened. Earth holds a special place only from the perspective of human experience. On the scale of the solar system, it is simply one of several planets orbiting an ordinary star. The Sun, in turn, is only one of countless stars in the Milky Way, and the Milky Way itself does not have unique traits that sharply separate it from other spiral galaxies. This way of seeing the cosmos formed slowly over centuries, and it changed how humanity defines its own place in space. Celestial bodies follow laws that can be tested regardless of size. Gravity acts the same in the fall of a stone and in the motion of planets, but across great distances its consequences unfold differently than in everyday conditions. Orbits, resonances, and long-term shifts in trajectories develop slowly. Yet they are what determine the stability of systems over millions and billions of years. A key feature of the cosmic environment is its unevenness. Even within a single galaxy, conditions can differ dramatically. Regions of active star formation are thick with gas and dust, while interstellar voids look almost transparent. These contrasts are not random. They reflect the balance between the birth and fading of stars, as well as the impact of explosive events that redistribute matter. We can observe space because information reaches us through multiple channels. Electromagnetic radiation spans a huge range, from radio waves to gamma rays, and each band reveals a different aspect of the universe's activity. Something that appears calm in visible light can be extremely energetic in X-rays or in radio. That is why modern astronomy almost always combines data from multiple instruments. Another role is played by high-energy particles that reach Earth's neighborhood. They carry clues about events that can be hard to detect in other ways. Their origin is not always traceable with certainty, so interpretations often remain open. In cases like this, science draws a clear line between what has been measured directly and what has been reconstructed using models. Step by step, a picture forms of space as a realm where stability and change coexist. Some structures persist for astonishing lengths of time. Others last only an instant by cosmic standards. This difference in duration does not make one phenomenon more important than another. It simply highlights the layered nature of processes that science tries to describe in a calm, careful language. That approach allows us to look at space without haste as a domain where each observation adds to the larger picture, but never exhausts it completely. Understanding space begins with accepting scales that have no direct analog in everyday life. Human thinking is used to distances we can imagine as a path, a travel time, an effort. In cosmic space, those anchors disappear. Even the nearest objects are so far away that picturing their arrangement demands abstraction, comparisons, and proportional thinking. The distance from Earth to the Moon feels large on a planetary scale. Yet, within the solar system, it is almost negligible. Light crosses that gap in a little over a second, making the speed of radiation a convenient measuring tool. Through light time, astronomy learned to connect space with time intervals without relying on imaginary rulers. The solar system is arranged so that planetary distances grow unevenly. The inner planets sit relatively close together, while the outer planets are separated by immense gaps. This pattern is not accidental. It reflects the conditions under which the protoplanetary disk formed and the balance between temperature, pressure, and available material. Science can create these processes in numerical models, even though some details remain debated. Beyond the solar system, distances become so large that the light year becomes the natural unit. It is not a measure of time, but a way to describe scribes through the distance light travels in 1 year. The method is practical, but it also reminds us that observing distant stars always comes with delay. What the telescope records is not the object now, but the object in its past. The Milky Way has dimensions that are difficult to grasp even with these units. Light needs tens of thousands of years to cross its disk. Within the galaxy, stars move along complex orbits around a shared center of mass, and the motion is so slow that a human lifetime cannot notice it without precise measurement. Changes become visible only by comparing data gathered by different generations of observers. The distances between galaxies are greater still. Galaxies gather in groups and clusters, and between them stretch regions of extremely low matter density. These voids are not absolute emptiness, but the number of particles inside them is so small that everyday ideas of a vacuum lose meaning. On these scales, the structure of the universe appears like a network, filaments of galaxies alternating with sparse regions. Cosmic expansion adds another dimension to the theme of distance. The space between faraway galaxies increases, and this increase is not simply their motion through space. It is a property of space itself, changing over time. This conclusion rests on many observations, though the details of interpretation are still refined within different cosmological models. To describe such scales, astronomy uses coordinate systems and conventional boundaries that do not exist physically. They are tools for organizing knowledge and communicating it. Recognizing that helps us treat sky maps and catalogs as instruments, not as literal reality. Cosmic scales also reshape our understanding of time. Processes that seem unbelievably slow ultimately determine the universe's appearance. The motion of galaxies, shifts in their shapes, and the buildup of mass in clusters unfold over intervals far longer than the lifespan of civilization. That is why science must combine snapshots of observation with theoretical frameworks that reach deep into the past. A calm sense of scale helps us drop the idea of space as chaos. Instead, it becomes an ordered system in which distances do not merely separate objects, they shape how those objects interact. Gravity, radiation, and the flow of matter behave differently across different levels of scale, and that is what makes the picture of the universe both rich and unfinished. Most of what science knows about space comes not from direct contact, but from the analysis of light. Light is the main mediator between the distant universe and human understanding. It travels through space carrying information about its source, the conditions under which it was produced, and the medium it crossed. Watching this process carefully allows us to see the cosmos not as an abstraction, but as a stream of signals that can be decoded. Light comes in many wavelengths, and the visible range is only a small slice. Radio, infrared, ultraviolet, X-ray, and gamma radiation fill out the picture by revealing phenomena eye cannot detect. Each range carries its own type of information. Cold gas clouds stand out in radio, warm dust becomes prominent in infrared, and extremely energetic processes are exposed through X-rays. Astronomical observation relies on the ability to spread light into a spectrum. This makes it possible to infer the chemical composition of stars, the temperature of their surfaces, their motion, and the physical state of matter. Spectral lines arise from interactions between light and atoms or molecules, and each line corresponds to specific energy transitions. These patterns are verified in laboratories, creating a reliable bridge between Earth's physics and cosmic observation. Shifts in spectral lines reveal motion relative to the observer. If a source is moving away, its light shifts toward longer wavelengths. If it approaches, the shift goes the other way. This effect underpins measurements of galactic speeds and became one of the key arguments for the expansion of the universe. At the same time, interpretation must remain cautious, because many physical conditions can affect the result. Light also does not always travel in perfectly straight paths. Gravitational fields from massive objects can bend its trajectory, producing gravitational lensing. Distant galaxies may appear distorted or even multiplied. These observations allow scientists to estimate mass that does not emit light directly, and they help map the distribution of matter in the universe, including components whose nature still has no complete explanation. Space telescopes expanded what we can do with light by moving observation beyond Earth's atmosphere. The atmosphere absorbs a large portion of radiation, so without leaving it, many phenomena would remain hidden. Orbital observatories capture cleaner signals in ranges that were once inaccessible. This did not make understanding faster, but it made it more consistent. Light also carries time. When we observe distant objects, we see them as they were in the past. Space and time become intertwined in a special form of knowledge. Observations of early galaxies let us reconstruct stages of cosmic evolution, though every reconstruction leaves room for refinement and alternative models. Not all signals arrive unchanged. Interstellar matter can absorb or scatter light, altering what we detect. Dust and gas introduce distortions that must be corrected, and dealing with those effects is part of astronomy's everyday work. It reminds us that data is not only recorded, it is interpreted. As the role of light becomes clearer, space begins to look less like a dark, silent emptiness and more like an environment full of messages. Science learns to read them slowly and carefully, acknowledge limits of knowledge and leaving room for what has not yet been explained. Gravity is one of the least noticeable forces in daily experience, yet it is among the most decisive in the architecture of the cosmos. It has no color, no smell, no form. Still, it is what prevents matter from dissolving into isolated fragments. Gravitational interaction organizes space gradually and relentlessly, forming stars, planetary systems, clusters of galaxies, and even larger structures. In the classical view, gravity is a force of attraction between masses. This works well for describing planets, moons, and most processes inside stellar systems. Such models predicted orbits with high precision and became the foundation of celestial mechanics. But as the scale of the universe grew, that approach proved insufficient to fully account for everything we observe. Modern physics also describes gravity as a property of space-time itself. Massive objects alter the geometry around them, and other bodies move within that curved structure. In this picture, a planet orbits a star not because it is pulled directly, but because it follows the straightest possible path in a curved spacetime. The idea is less intuitive, but it agrees with many precise observations. Gravity affects not only matter, but also light. Light beams bend near massive objects, creating distorted images of distant galaxies. From this, astronomers can estimate the mass of objects even when they emit little or no light. Through gravity's imprint, science finds evidence of hidden components of the cosmos. On the scale of galaxies and clusters, a mismatch appears between the amount of visible matter and the gravitational effects. Objects move as if far more mass exists than we can observe directly. This discrepancy led to hypotheses about an additional invisible component of matter. Its nature remains under investigation, with interpretations ranging from new particle types to revisions of the laws of gravity. Gravity also drives star formation. In cold gas clouds, small irregularities slowly grow, and matter begins to collapse under its own weight. The process can take millions of years. Only after certain conditions are reached do thermonuclear reactions ignite and a new star is born. Stars then influence their surroundings. Gravity again remains the key factor of stability. The balance between internal pressure and self-weight sets a star's lifespan and evolution. When that balance breaks, different endings unfold, and each leaves a distinct imprint on cosmic structure. On even larger scales, gravity shapes the cosmic web, a network of filaments and voids where galaxies are arranged. Observations show matter is distributed unevenly, forming gigantic structures that are hard to imagine. This distribution reflects early conditions in the young universe and the slow growth driven by gravity over time. The study of gravity continues to expand our picture of space. Measurements of subtle light distortions, galactic motions, even ripples in space-time let scientists test theories with increasing precision. Yet many aspects remain in the realm of hypothesis, and gravity still retains features of a phenomenon not fully revealed, even at its most fundamental level. Observing the universe depends not only on visible objects, but on registering many kinds of signals arriving from space. Light, radio waves, high-energy particles, and fluctuations of space-time carry information across enormous distances. Most of these signals fit well within known physical models. But from time to time, events are recorded that do not have a single clear explanation. One example is extremely intense, brief radio bursts coming from beyond our galaxy. They last only a fraction of a moment, yet in that instant they can release energy comparable to a star's output over a long period. Their appearance seems abrupt, and for a long time the mechanism behind them was unclear. Observations show that some repeat, while others occur only once. Studying such bursts is complicated because they pass through intergalactic space, which alters their properties. Frequency-dependent delays, scattering, and distortion provide extra information about the medium, but they also make the source harder to interpret. Models suggest several possibilities involving extremely compact, highly magnetized objects, yet no single explanation captures every observed feature. Another example involves cosmic particles with energies beyond what known acceleration mechanisms easily produce. They reach Earth from directions that cannot always be tied to specific astrophysical sources. Their extreme energy creates serious challenges for standard origin models. It is not clear what processes could grant particles such properties without breaking known physical limits. Investigating them requires complex detectors and long observation times. The number of recorded events is small, which makes statistics difficult. Every new detection adds data, but it also underlines how incomplete the overall picture still is. In the scientific community, both conventional astrophysical and more exotic hypotheses are discussed, yet none has gained final confirmation. A separate group of signals involves ripples in spacetime produced by extraordinarily powerful events. Their detection became possible only through ultra-precise measurement. These observations opened a new way to study the universe, independent of electromagnetic radiation. At the same time, some recorded waveforms show characteristics that do not perfectly match theoretical expectations. There are also signals whose sources remain unidentified even after years of monitoring. They do not repeat reliably, do not align neatly with known objects, and do not display stable properties. Such phenomena force science to reconsider how it classifies cosmic events and to accept the limits of existing approaches. Sometimes the difficulty lies not in the signal itself, but in interpreting the background against which it appears. Space is filled with radiation of many origins, and separating an unusual signal from the blend of familiar processes can be extremely hard. This demands not only technical solutions, but careful statistical analysis that reduces the risk of false conclusions. Discussions of such signals tend to be restrained. Researchers work to separate observed data from interpretation. An unusual event does not automatically mean fundamental laws are broken. Often it points to gaps in knowledge or to processes not yet included in current models. Studying these signals slowly shifts the perceived boundary of what is possible in space. They show that the universe can behave in ways that are difficult to predict from what is already known. At the same time, each new observation reinforces the importance of patience, because the path from a confusing signal to a scientific explanation is usually long and complex. In cosmic research, what is not detected matters almost as much as what is. The space between sources can seem empty at first glance, but in reality it is filled with faint signals, instrumental noise, and background processes that accumulate in data. Distinguishing a meaningful phenomenon from a random fluctuation requires long analysis and cautious conclusions. One reason is the limited sensitivity of instruments. Even the most advanced telescopes and detectors operate within specific ranges and thresholds. Signals below those limits remain invisible. That does not mean the processes do not exist, only that science does not yet have direct evidence for them. Cosmic background adds further difficulty. The relic radiation, interstellar dust, plasma, and magnetic fields form a complex medium that modifies signals from distant sources. Information can be distorted, partially lost, or blended with other components. Recovering original characteristics requires models with many variables, some known only approximately. Special attention is drawn to periods of silence, when expected signals do not appear. In some observations, theory predicts radiation or particles, yet instruments detect nothing. These mismatches force scientists to recheck both theory and observation methods. Sometimes the cause is incorrect assumptions about conditions at the source. Sometimes it is the influence of the medium between source and observer. Silence can have different origins. In some cases, it reflects temporary changes in an object's activity. In others, it is geometry. The emission is not directed toward Earth. Sometimes an expected signal is simply masked by stronger processes. Telling these cases apart requires comparing many independent observations. Data processing methods become central in the search for weak signals. Modern science uses statistical approaches to find patterns in huge data sets, but these methods depend on assumptions. Changing selection criteria can cause a signal to appear or vanish in analysis. That is why any claim demands verification by independent teams. Another powerful tool is comparing data across different ranges. A signal too faint in radio might appear in a different kind of radiation. This reduces uncertainty and clarifies physical conditions at the source, while also emphasizing that no single method gives a complete picture. Scientists often stress that the boundaries of observation keep shifting. Each new generation of instruments opens its access to signals that were once unreachable. What recently looked like a lack of information can later become a source of new data, but the process is gradual and not always predictable. The silence between signals is a reminder of the limits of human knowledge. It is not emptiness, but a space of uncertainty. Inside that uncertainty grows the need for new approaches, more sensitive tools, and a disciplined attitude toward interpretation. Recognizing these limits helps science move forward without losing contact with what observation actually supports. In long-term observation, a special place belongs to signals that repeat, yet do not fit familiar models. Repetition is usually taken as evidence of a stable source or a cyclical process. But in space data, there are cases where regularity coexists unpredictable features, making explanation difficult within known theory. One challenge is variability. A repeating signal may keep its overall shape, but change in intensity, duration, or spectral traits. It can feel as if the source follows internal rules we do not understand. Science must separate true physical change from effects caused by observation conditions and instrument behavior. Repeating signals often revise our assumptions about how stable cosmic objects really are. Stars, compact remnants, and regions of strong emission were once thought to behave predictably. Accumulated data showed that even these systems can display complex dynamic, sometimes due to internal processes, sometimes due to environmental influence. Periodicity becomes a central question. If a signal repeats at equal intervals, researchers look for mechanisms tied to rotation, orbital motion, or oscillation. Some cases show only approximate timing, with deviations that resist simple description. That pushes analysis towards statistical approaches rather than neat deterministic models. A further complication is the blend of repetition and suddenness. A signal may disappear for a long time, then return without a clear trigger. That challenges the idea of continuous activity. Some researchers suspect hidden system parameters that are not directly measured. A neutral stance toward alternative explanations is essential. For repeating signals, hypotheses range from well-known physical processes to more speculative models. The scientific method is not about choosing the most exotic option, but about gradually eliminating explanations that contradict observations or fail to match other data. Comparing different repeating sources reveals both shared traits and major differences. In some cases, similarity suggests a single class of objects. In others, superficial similarity hides very different physical origins. This kind of analysis takes time and requires many observations gathered under varied conditions. Theory matters here, but it has limits. Models help outline possible mechanisms and test them for consistency, yet none is treated as final. A shift in assumptions or the arrival of new data can dramatically change interpretation. These phenomena underline that even regularity in space does not guarantee simplicity. Sometimes research reaches a boundary where more data does not immediately turn into understanding. Signals can be recorded, described, classified, yet their origin remains unclear. In such moments, science works not with answers, but the limits of its instruments. A key limit is incomplete observation. Any signal is registered within a certain band, with a certain precision, under specific conditions. What lies inside those boundaries does not vanish, but it does not enter analysis. Interpretation is always based on a fragment of reality, not its full description. This awareness encourages caution with dramatic claims. Another boundary is dependence on theoretical models. Even the most careful analysis relies on ideas about how matter, energy, and spacetime can behave. If a signal does not fit those ideas, tension arises between observation and explanation. Often this does not indicate error. It indicates that a model captures reality only partially. Language itself is also a problem. Complex phenomena must be described using terms with established meanings, which can create the illusion of understanding where it does not yet exist. A label or classification can be mistaken for an explanation, even though it is only a marker that guides further work. Some signals remain at the edge of modern detection. They may be too faint, too rare, or too brief. In those cases, even confirming they exist becomes difficult. The scientific community must balance caution with openness, not dismissing observations, but not assigning them premature significance either. Time plays a special role. Some signals go unexplained for years or even decades. A technological breakthrough, new analysis methods, or theoretical development can suddenly make them meaningful. But the opposite can also happen. An early explanation later proves incomplete or wrong. In this context, uncertainty stops being a flaw and becomes part of the process. It marks zones where knowledge is still forming. Instead of forcing closure, science keeps questions open, allowing different approaches to coexist. That slows the path to final answers, but makes it more stable. Unusual signals remind us that the observable universe is more complex than any single scheme of description. They do not always overturn fundamental ideas, they continually test them. And even when an explanation is delayed, there is value in the quiet interval between detecting a signal and understanding it. In that silence, there is space for careful thinking. No rush is required, and no final formulation is necessary. There is only observation, analysis, and a willingness to accept that some questions may remain open longer than we expected.